Good afternoon, everyone. First of all, I would like to thank Lydéric Bocquet for giving me this opportunity to present the work we are carrying in my group in Laboratoire Coulomb. So all over the year of courses of Lydéric, I think we have heard how much important is the field of nanofluidics, of course, for us physicists, but not only, it goes well beyond. But there is a big paradox for me, is that it is extremely difficult to access it experimentally. And this is why we envision that mechanical resonators can have a role to play in this field, and we will develop now the reason why. So I will start with this paradox, this difficulty to do nanofluidics, although it's a very interesting field, and I will slowly move towards the use of nanomechanical resonators to probe the physics of nano-confined fluids. So all along the different courses, and especially in the open course of Lydéric Bocquet, we have seen that nanoscale confined water is something that is extremely important for us physicists, both from a condensed matter point of view and, of course, from soft matter point of view. But we have also seen that it goes well beyond physics. There is a lot of societal challenge that can be addressed with nanofluidics. Lydéric spoke, for instance, of the possibility to generate blue energy. So this is a renewable form of energy with osmotic devices that include nanochannels. And I think there is another big societal challenge, is the access to clean water. For me, it's the first year I hear about winter drought. So I think even in France, we'll start to miss water, and we need new solutions to give access to new form of water, from salty water or from depolluting water. And of course, it can also have implication for biology and medicine if we can cure some of the diseases that are related to the aquaporins. So in this field of confinement of water, there is one system that seems very nice to me. It's the carbon nanotube. One of the reasons why it is an interesting system to do confinement, it's because it's a nearly perfect object. From the point of view of physics, it's a nearly completely crystalline structure with very little density of defect, so that's quite nice. But also for free comes a very small dimension of the hollow core, which means that we can have access directly to ultimate molecular confinement with those nanopipes. They are now technologically mature, let's say. We can synthesize them, we can characterize them. And of course, we have seen that there is already a lot of physics demonstrated in those systems. So my aim is not to go all over the effects we have already heard about, but I want just to emphasize the fact that it is both very rich and very often it is counterintuitive phenomena that we observe for the confinement of water inside nanotube. What we know is that, for instance, water can form structures inside the nanotubes. Those structures, they are unique in nature, although it stays liquid. Going with this unique structure, there is the fact that we can feel the nanotube, which was not obvious at all. If you remember, it's a hydrophobic system, so we would not expect the feeling, although it happens spontaneously. And from the point of view of the motion, of the transport of particles, there can be concerted motion of particles, although we're working at room temperature. Maybe down to the smallest diameters, there could be no friction for the flow. That would be quite interesting, and this is something that was started to be seen experimentally, while here reducing the diameter, the permeation for the nanotube is really getting high, and only for carbon nanotube, so it really motivates the use of those nanotubes. So overall, there is some very fast flow of water happening inside carbon nanotube. Now, this is the motivation to study this field, but there is a big challenge. It is to access experimentally something, because we are speaking of few 100,000 molecules confined in a nanotube. We need to have a method that is sensitive enough to probe this physics. And this is where mechanical resonators, they really have a role to play. It was shown actually in the group of Adrien nearly 10 years ago that mechanical resonators made of carbon nanotube, they can sense masses down to one single proton. It's a yoctogram, that's 10 to the minus 24 grams. So this is, for me, the way to lift this paradox in nanofluidics, is to use those mechanical resonators to access the physics of confined water. What comes also with mechanical resonator is that you naturally work with a single nanotube, and therefore you can link the diameter of the confining matrix to the different effects you're measuring. So you don't work with powders or anything like this. You work normally in vacuum, which means that you will have no water outside. This is quite important, we know, from an experimental point of view. But also there are no interaction with the substrate, which can really blur the effect that you want to see. And you can work basically with any kind of carbon nanotube, any metallicity or chirality of nanotube, and therefore you can address all the different hypotheses that are behind the fast water transport. So if I get a little bit more into the detail, already how do we access to the structure, the static properties of water? With a carbon nanotube, you can measure the mechanical frequency of the nanotube empty. And then if you selectively open the nanotube and expose it to water, then you will get a downshift of that frequency that will be proportional to the mass of water that you encapsulated. Now, provided that you know the geometrical parameter of your nanotube, which is experimentally feasible, you can link this mass to a density, and then you can compare with molecular dynamic simulation and find the actual structure of the water confined inside the tube. So that's nice, you can do structures, but you can also do flows. If you imagine that you dope now your water with a heavier particle, let's say a tracer, while this tracer will translocate through the nanotube, it will locally change the resonance frequency of the nanotube resonator, and this will give you access to a sort of time of flight of that particle, and therefore you can again calculate a flow. So this is really interesting because you can do both structure and flow with the same system, and both with molecular resolution. Last but not least, because we work in a mechanical configuration, we immediately have access to the possibility to excite a lot of mechanical modes, all these guitar string modes, but also Raman active modes. And therefore, this is quite useful to systematically verify the hypothesis of the fast water flow that I'm reminding here. It might be linked to the structure of water, it might be linked to the curvature of the nanotube, the phonons, or really the different modes of vibration, or the electrons through the quantum friction phenomena. So this is the aim. Now the question is, how do we achieve it? And we immediately arrive into a big problem, is that we want to work in vacuum with fluids, which is not straightforward at all, especially at the nanoscale. So basically, this is a sketch of our problem. We want to put water inside the nanotube, but mechanical resonators don't like to be in air or in gas. So we need to make a wall here that is completely leak tight. It has to be also chemically inert and, of course, vacuum compatible. Last but not least, you want to work with nanoscale systems, so you have to make it as small as possible, keeping this leak tightness. And of course, the process to make it should not destroy the material that you have on the surface, which is, for instance, not straightforward with the standard in microfluidics, which is PDMS. So there is one candidate that we tried to evaluate here. It's SU8. That's an epoxy photoresist that then you can pattern by photolithography, so you can make it quite small. That's great. It's already used in MEMS community, so we know it's vacuum compatible. And it's also used in some applications in microfluidics directly. I mean, not just as a mold for PDMS. And therefore, it is chemically resistant to water. But there are still some open questions, and this is the questions I will address right now. What are the minimal processable dimensions? And I mean really down to the moment that you have fabricated a leak-tight channel. What is the level of leak tightness? Can you assess a level of porosity? And does the device degrade over time? Because as experimentalists, we like to keep our good devices for weeks and months, but this is usually not the case with PDMS that survive maybe 1 month, if you're lucky. And we want to go down to the ultimate test for us, which is doing fluidics under vacuum. So assessing the leak tightness to water, it's actually not that straightforward. We decided to take the burst pressure technique, in which we will fabricate one reservoir of SU8. So this is the side sketch, and you can see here the pictures with the SU8 wall being highlighted. And then we will press the water inside that reservoir, and we will optically inspect for the leaks. So this is a mono reservoir configuration. Actually, it's very on-off. Either it sustains the leak, the water pressure, sorry, for several hours, either it leaks. So I'm plotting here the results for 10 devices of 60 micron width, and you can see that there is a distribution of pressure that can be sustained by our different devices until they break. And this is so the distribution is plotted here from minimum to maximum, and this is the mean value for each of the different dimensions that we tested. And what we realized is that SU8 can make leak-tight walls up to 5.5 bars, which is quite good and quite better than the standard in the microfluidic community, the PDMS. But also the tightness does not seem to be limited by the wall thickness, as there is no clear trend of decrease as we decrease the wall thickness. So as I said, we wanted to assess also the level of porosity in this system, and then we moved to the technique that we thought was the most sensitive to assess it, is electro-osmotic transport. Actually, this is already used to measure ionic current inside carbon nanotube. In the lab, we do a carbon nanotube of 40 micron long, so you see you can measure very little signals with this technique. So you just need to readapt a little bit your system to have a two reservoir configuration in which you can put salts and two AgCl electrodes. And this is very standard. We apply a bias now, and we push the ions through the SU8, and we measure a current. So this is a typical patch clamp experiment from which I will just extract now the conductance. So I'm plotting here the results for different devices of two different dimensions of the conductivity as a function of the concentration of salts. What we see is that although there is a factor 2 in the dimensions, we get very similar conductivities. If I take the device number SP7, so the smallest dimension one, we see that the conductivity is nearly flat with concentration, which indicates that there is no nanoporosity. If I take the largest device, we see that we have a certain slope, but it is below 1. So this is also not following Kohl's law, so therefore we can say that this is not bulk conductivity happening into this wall. Now, an important point, as I mentioned earlier, is to verify how long you can use your device. And this is what we did for these 3 different devices that we recorded regularly on a scale of nearly 4 months. And what you can see is that, okay, we normalized all the devices by their starting point so that we can compare them. And what we can see is that although there is a lot of scattering into the conductivity, there is no just a slope of increase, and there is no trend over the several weeks. And therefore, we can say that there is no significant degradation over time. If you take PDMS, you will see that it just increases like crazy over a few weeks. So these are the conclusions here. We have not identified any obvious porosity, and there is no significant degradation on the scale of several months. Now, I'm just stepping 1 second to compare a little bit the performances with PDMS. In the lab, we use a lot PDMS for microfluidics, as I said, to measure ionic transport in nanotubes. And we found that in most cases, our SU8 devices, they have a similar or even better conductivity compared to PDMS, so the standard in the microfluidic community. So my message here is that probably we can all move to this kind of material. It simplifies a little bit your fabrication, and it does not require any plasma activation, so you can really work with fragile materials. Now, last but not least, I said we wanted to work into vacuum, so I have to show you the data of what's going on under vacuum. What we did is we took again our first device, we put it into our vacuum chamber, and it is connected still outside to water. And we pump over this guy down to secondary vacuum. What we checked first is that the SU8 was not outgassing, that was expected, but also then we pressed, so we pushed water inside the reservoir, and we verified if the pressure was rising at that moment. And we found no pressure rise, which means that the leak rate, the upper bound, which is set by the sensitivity of our gauge, is in this range, which tells you nothing, but usually it is considered that a system is completely tied to vapor if it reaches 10 to the minus 3 millibar, and we are below. So in the end, my message here is that both SU8 is compatible with vacuum, it does not outgas, but also we found absolutely no gas-water permeation through the SU8. So this is the partial conclusion on this part. We found that SU8 is leak-tight to water, even for high pressure, and for very small dimensions. We have not identified any porosity in it, and the devices, they can survive for several months. Also, I didn't show, but the SU8 is electrically non-conductive, so it's quite important for us to measure the mechanics later. And overall, as I said several times, the SU8 processing just takes a small heating to make the bonds, and therefore it meets completely the requirements to work with sensitive surfaces. Now, my second step is to show you how the mechanical resonators are made and how sensitive they really are. So this is how it looks like the system. We have here two electrodes that act as source and drain, and the bottom gate here in the bottom of a trench. So this is an electronic transistor. And if you zoom a lot in the middle, you will get to see this suspended guy that is our carbon nanotube mechanical resonator. So how do we measure the motion of such a tiny resonator? Well, we have an electronic setup to do that. What I want to emphasize is the fact that the nanotube is suspended over a gate, and so it's called a capacitive coupling. It means that any motion of the nanotube will translate into a current, and this is what we detect. We detect current typically in the order of femtoamperes here. And we have the possibility not only to detect the current, but also to drive the resonator applying an AC voltage to the gate. So how do the signal look like? This is the typical Fano line shape that we find when we hit a resonance, so when we sweep the frequency, okay, and we measure the current. And to verify that this is really a mechanical resonator, you can apply a DC bias, then you induce tension into the nanotube, and you get electrostatic hardening, so you see that your mechanical frequency goes up very quickly. So this is the typical behavior of a carbon nanotube resonator. Okay, well, I said that nanotubes are really sensitive. The question is, what is sensitivity for a mechanical resonator? The central idea is what is the minimal mass that you can detect? How do you define this sensitivity? The true story is that if you look at the resonance frequency of a mechanical resonator, any resonator actually, as a function of the time, you'll get some jumps, you have some jittering of the resonance frequency. And this defines you an effective sensitivity. If you like to get a signal-to-noise ratio of 1 with an added mass, you have to go outside these boundaries. So this is the definition I will take for the mass sensitivity. There are several ways to evaluate the mass sensitivity. The most maybe intuitive way is to do it in an open loop, which means that you just record the phase of your resonator and you translate it into an instantaneous frequency, knowing the baud response of your resonator. But we will see that there is also a possibility to reuse this phase information and to feed it back into the drive frequency. So I'm plotting here the first case, the open loop, where we measure the phase of the resonator as a function of the time. I can convert this into an Allen deviation, which is basically a statistical variance. And then from this Allen deviation, I can compute my mass sensitivity. And with this actual set of data, we found a sensitivity of 10 zeptogram, which is 10 to the minus 21 grams. Now, if I close my loop, I have directly access to the mechanical frequency of the resonator. I can again compute my Allen deviation and my mass sensitivity, and I find a sensitivity of 5 zeptograms, which means a factor 2 improvement by a phenomena that is well known, which is the phase locking of the resonator. So, okay, that's nice. This is the first device that we measured. Actually, we went down to 3 zeptograms a bit later. I just didn't have the data. And then we took another device. We measured it the first time, but also in the middle of our experiment, we had to move our labs. So we had the opportunity to measure the same device in different conditions, and we had more time also to push a little bit, and we went down to 70 yoctogram. So the mass of roughly 10 molecules of water. That's really nice because to address the questions of nanofluidics, you really have a system that has a very good resolution. It places us 2 orders of magnitude better than what was done several years ago at room temperature, and we are only 2 orders of magnitude away from the world record, but that was done in cryogenic environment. So you may ask now, okay, what is the limit sensitivity you can do? Can you do 1 yoctogram at room temperature? Well, not that far, probably. One thing is that I have to remind you, we work at room temperature, and therefore any molecules that would be on the surface of the nanotube would diffuse, which would contribute to noise because it will change the effective mass of the resonator. The way to see it is to take the same nanotube device and to measure it after passing a very large current through the nanotube, therefore doing a current annealing to remove any impurity. And we see that the same resonator has a sensitivity improved by a factor 2 after this current annealing. So really one of the main mechanisms that was limiting the sensitivity was particle diffusion in this case. And we can pinpoint also a secondary mechanism, which is adsorption-desorption from the gas phase. We are in secondary vacuum, but that's not ultimate vacuum. That could occur on random traps, and with the current annealing, we can remove part of those traps. Okay, but then when you have done the current annealing, what is the limit? If we do the Fourier transform of this frequency fluctuation, so we see that there is a 1 over f slope here. We were expecting actually something more flat, probably, for frequency fluctuation. But coming from electronics, 1 over f noise, you start to think about Johnson-Nyquist noise. So we investigated noise coming from the different source of our setup. So this is, in essence, what is sketched here on this plot. In black, you have the actual nanotube sensitivity. In green, we measured one of the most important source of noise, which is the noise of the DC source, okay, because it changes the resonance frequency. And we see that this is very far from the nanotube sensitivity. Everything here is additive. We also measured the thermal fluctuation. Actually, there is a little bit of drift in time. This is because over several hours or over days and nights, you have change in the lab temperature. This, you cannot get rid of it. But still, this is not the main contribution. And we also looked if the Brownian motion, the thermomechanical noise, could be the limitation, because we work at quite high temperature. And this is this data point. Well, actually, this is calculated, but still we see that there is a 1 order of magnitude difference. So we are not yet limited by such fundamental sources of noise. So coming back to the gas and the interaction with particles, we tried to take actually the opposite of what I did before by increasing the number of particles in the cell. So we wanted to verify if it had any influence on the sensitivity. So for this, we injected dry nitrogen for technical reasons, and we would expect that the quality factor degrades with the pressure, and therefore the sensitivity does. And also we would expect more interaction with the gas phase, adsorption, desorption, and momentum kick from the gas. But this is actually not what we see. We found that the quality factor is quite stable with increasing pressure, and we found that the mass sensitivity stays more or less the same as a function of the pressure. What is very interesting to me is that it seems it's not limited, and I would be very interested to push towards room pressure, because maybe we can keep this exquisite sensitivity up to ambient pressure and room temperature, sorry. Last but not least, we can also make the particles diffuse a little bit more on the surface without changing their density. If we just change the temperature of the cryostat, we heated a little bit our system, but it seems that at the highest and the lowest temperature, the two sensitivities are exactly the same. So after the current annealing, it means that there is no more particles on the surface, and the sensitivity is not diffusion limited now. So this is my summary on nanotube resonators. We found an exquisite sensitivity of 70 octogram. This is 2 orders of magnitude better than what was done in the literature. It is reproducible on the same device and on different devices. We have not found the limitation so far. It's not thermomechanical or our setup. It seems that the sensitivity could be preserved by increasing the cell pressure, maybe even up to ambient pressure. And the last step we took in the direction to use our mechanical resonator is to fill our nanotubes, but just with standard electronic configuration. We did this for 2 reasons. This is because the electron transport is known to be a very sensitive tool for the physics of water adsorbed outside the nanotube, but says there is little known for what is going on inside. And for us, it was important because it was a way to verify that we could still measure mechanics with a filled nanotube. We need actually the electronic transport to be preserved to do that. So the system is very simple. We grow carbon nanotubes, and we deposit electrodes on top of it. So we can measure the conductance by taking the backgate substrate as the modulator of the channel, and this is the typical nanotube conductance that we obtain. And now, because we grow our nanotube, at the beginning they are closed on both sides, so we can selectively open them by Joule heating, just by fusing some of the extremities. So it means that I will be able to show you data of the same nanotube device before and after opening. And in this presentation, I will focus on devices that we identified as single-wall nanotubes, but also individual nanotubes, not in bundles, because it complicates a lot the adsorptions. Okay, so there are 4 possible mechanisms to explain the interaction of electrons with water. The first one is it's called here gating, but it's more straightforward to say doping. So it would change the conductance by shifting the neutrality point. You can tune a little bit the Schottky barriers. So you just essentially change the balance between the 2 branches. If you have any capacitive effect, you will just modulate less. And you can also degrade just the mobility of your transistor with scatterers. So to track this, we have several metrics: the on conductance, the slope, which is an image of the mobility, and the position of the neutrality points. And very quickly, we realized that this is the guide that is important to assess the physics of water. So we do a lot of treatments. We expose to air, to water. I will come a bit more on it. So, sorry, I forgot to say this links us to doping effect. I got several times the question, but what about the capacitive effect? You have liquid media such as water that has a high dielectric constant. Okay, so we can measure the conductance of the nanotube in air, but also in different media with different dielectric constants. And then you can rescale the VG axis, which is your experimental axis, to get everything normalized by the dielectric constant. So we did this for different materials, and if it was a capacitive effect, all the curves, they should fall back on top of each other. So the main conclusion here is that the capacitive effect is not dominant at all. Okay, so coming back to our nanotube, we measured first the device unopened in different conditions. So here immediately in air after a long time in case there is some kinetics. We put the device under vacuum, secondary vacuum, and we current anneal our device to clean everything that should be at the outside, including water. And we keep this under vacuum. I can do this several times, and also I can do the same for the nanotube that is open. So these are the open symbols. And you see immediately that in vacuum and after annealing, there is now a difference between the exact same device, open and closed. So essentially, we see 2 plateaus for the unopened case and 3 plateaus for the open case that we can link to different positions of water. The secondary vacuum seems to remove the confined molecules because we don't see it in the unopened case, while the current annealing removes the outside molecules. Importantly, at the scale of our experimental measurement, we see that the filling and the adsorption outside is completely spontaneous and instantaneous. We also verified that the same behavior was happening with wet water, okay? So, with liquid water, not only with air. Well, you can see that this is exactly the same here. And again, we get our plateaus for vacuum and current annealing. And we also verified that everything was the same with any kind of nanotube, any metallicity. I'm showing here the data for both a semi-metallic nanotube and a semi-conducting nanotube, and we see that they have essentially the same behavior with 3 plateaus. So this being said, you can go a little bit further, and these are very preliminary data where we try to do kinetics, but also thermodynamics of the emptying of the nanotube. So this time I'm taking a nanotube that is a little bit longer in order to make the things more visible. And what we did is we progressively, so at each dashed line, we decrease the pressure. But in between, we stay at the same pressure, and we just measure on a regular basis what is going on in the system. And what we see is that going from one stable position to another takes some time, roughly 1 hour. And there is, of course, several plateaus that we can link to different adsorption sites. So probably the water outside, the water inside the tube, but also the water at the pore entrance. Okay, so this is my summary for the scientific part. We have seen that water adsorbed outside and inside can be distinguished electrically with nanotube transistor. The main mechanism is doping, and we aim to confirm it with Raman scattering by tracking the G-band. We have seen that the filling is spontaneous on the time scale of our experiment, which is roughly a few minutes, while the emptying is very long and can take up to 1 hour. We have verified that humidity has a similar effect as exposure to bulk water, and also that the response to water is completely independent of the metallicity of the nanotube. So it's time for me to conclude. I would like to acknowledge the people that worked on this topic and also the different funding sources that we benefited from. And this is now the conclusion of my talk. I showed you that SU8 microchannels can allow you to work with fluidics under vacuum with very good performances, even better than the standard in the field, PDMS. I also showed you that nanotube resonators shows exquisite sensitivity at room temperature, which was unexpected, and with a sensitivity value of 70 octogram. And I also showed you that CNTFET are a useful tool to distinguish the effect of water inside from the water outside the nanotube through doping mainly. So in conclusion, I hope you are now convinced that nanomechanics is a promising tool to address the questions of nanofluidics, those questions, as we have seen all over the day, being very, very difficult to answer experimentally. Thank you for your attention.